Well folks, Sean here from SMD Methods. You're very welcome into this video. In this video I'm going to look at solving a system of linear equations using the Gauss-Seidel method. Now the application that I'm looking at comes from a 2026 Numerical Methods for Engineers module paper out of a BEng course, and question 1 lays out a system that is described by an infinitesimally thin heated plate with temperatures applied to the 4 edges of the plate, and the task is laid out here in part A is to solve for T11, T21, T12 and T22, which are the internal nodes on this plate. Now part A says that the solutions to these should be found using a centered differences approach, or as it's called here, a centered finite divided differences model, central differences approach. So effectively it's a discretization of this kind of heated field, which would otherwise be solved analytically using Laplace's equation, I believe, for the heat transfer across the plate, which is a partial differential equation with one part in temperature being a function of time, and then the other function being space, whether it be x and y or x and y in this infinitesimally thin plate. We are given a hint in part A for the form of the equation, which doesn't itself solve for T11, 12, 21 or 22, but it gives us a starting point, and what it does is it gives an indication of what the centered finite differences approach may look like. So what it basically is saying that the temperature at any node is going to be equivalent to the average of the temperatures around it. So if we are doing T11, for example, T11 is in the center T01 and T21, but it's also in the center T12 and T10. So the temperature in T11 should be the average of the temperatures at these 4 points around it. That's what the theory says. So, and that's what's basically laid out here, albeit it's in a form that doesn't lend itself to show that it is the average. If you did bring this minus 4T11 over to this side and then plus 4T11, and then you divide it by 4, you would have that T11 is indeed equal to 1/4 of T21, T01, T12 and T10, which are the 4 nodes around it. So the proposal on this is to take this whole entire question and bring it into OneNote. On a page here, let's call this Gauss-Seidel. This is 2026 Numerical Methods for Engineers, and that was question 1, I believe. Let's paste that in. I'm going to shrink this up a wee bit. Just move the mug over to this side. Bring that back up to here. All right. So what I'm going to do, I'm going to bring it brave and small here, bringing it on over here a little bit more, just so I have a little bit of room to the right hand side in which I could write these equations, and try to keep these all as much as I can on a single screen. So part A is given here. It's looking for the equations to solve for T11, 12, 21 and 22. So what I'm going to do is I'm just going to write these equations up similar to the hint that's given to us here, the first equation, T01 plus T12 minus 4T11 plus T10 is equal to 0. Alright, so that is clearly solving for T11. I'm going to move over to T21, and I'll say that T31 plus T11 plus T22, which is the one above T21, minus 4T21 plus T20 is equal to 0. Next one, I'll go up to T22, so I'll start to the right, T32 over to the other side to the left, plus T12, go up above it, which is T23, minus 4T22 is it itself, plus the one below it, T21, is equal to 0. And finally over for T12, let's go to the right, which is T22 to the left, T02 above, T13, it's itself 4T12 plus T11 is equal to 0. There's 4 equations. Now none of them solve for T11. T12, T21, T22. So let's rearrange them around. So this is going to be our solutions. Rearranging the first one for T11, we'll have T11 is going to be equal to 1/4 of T21 plus T01 plus T12 plus T10. Nice. Next one, we're going to solve for T21. T12 is what's asked for next in order. So yeah, let's just keep it in order because it might make it a little bit interesting when we look at part B. T12 being the next one is going to be this bottom one we'll solve for, which is going to be equal to 1/4 of T22 plus T02 plus T13 plus T11. Okay, the next one we're asked for here is T21. T21 is going to be the second equation for T21. So T21 is equal to 1/4 of T31 plus T11 plus T22 plus T20. And finally then, we're asked for T22. T22, which is the third one here, is going to be equal to 1/4 of T32 plus T12 plus T23 plus T21. That's it. So they are the four equations solved for T11, T12, T21, T22 as per part A. And using, oh look, that's one a wee bit off. This will pull it back. It's okay. Alright, so that's part A. Right, now part B is about show that the system of equations formed in part A is diagonally dominant. So diagonal dominance. For diagonal dominance, we need to diagonal dominance is relevant to a square matrix. There's nothing obviously matrix about either these set of equations up here or these ones. So what we're going to do is we're going to rearrange it to put it into the form of the following here, which is AX is equal to B. Okay. So we put this in the form of AX is equal to B. A is going to be the coefficient matrix, and the square matrix that we're going to try to prove is square, or is diagonally dominant. Apologies. So rearranging this, what we'll actually do is we're going to use these up here. Could be the best starting point, but what we'll also need to do is we're going to have to determine what the forcing function is. The forcing function is going to be that column vector B. So AX is equal to B really has a coefficient matrix multiplied by a system reaction or system kind of response to a forcing function, which is B. And the response in this is going to be T11, T21, T22, and T12, i.e. how the plate is going to hit. This is the response to the forcing function. What is the forcing function? Forcing function is them temperatures that are applied to the four edges of that plate. So I think what we'll do here first is let's set this up, these equations here, and plug in the values where we can. So in our first one we have T21. So T21 does not have a boundary value here. All right, the only ones with boundary values are going to be T13, 23, 32, 31, 10, 20, 01, and 02. So those are the nodes that are on the edges of the plates. Two of them are on side A, two of them are on side B, two of them are on side C, and then two of them are at 0 degrees, 32 and 31. So let's just see, 32 and 31 are at 0 degrees. Let's go red here, which is the hottest one, which is side C. T10 and T20 are at 200. B is at 150. Let's go a wee bit cooler. T there at 150. And then side A, 13, and go green on this because yellow doesn't show up so well, are on side A. Side A is at 100 degrees. Right? Notice this here is the 0 degrees, which is written there. All right, so let's write in some equations here. Let's start up with starting with this first one here. So T21 itself, T21 does not have a temperature just yet. T21 plus TO1 does have a temperature. TO1 is at 150 degrees, plus 150, plus T12 doesn't have a temperature, minus 4T11, which doesn't have a temperature, plus T10. T10 does have a temperature. T10 is 200 degrees, plus 200 is equal to 0. So what I'm going to do is I'm going to rearrange this, and I'm going to take the forcing functions, the temperatures that are on the boundaries, and bring them over here to the right hand side, and I'll be left with T21 plus T12 minus 4T11 is equal to minus 350. Okay, that's one. Okay, the next one here is the T31. Now T31 itself does have a temperature. So T31, let's skip space, 0. Right, that's on the purple, T31, plus T11 doesn't have a temperature, is an internal node, plus T22 is an internal node, minus 4 T21 is an internal node, plus T20 is a boundary node. T20 is at 200 degrees. Again, plus 200 is equal to 0. Rewriting that, we would have T11 plus T22 minus 4T21, and that's equal to minus 200. All right, next one. Go for T32. So T32 is on the boundary. T32 is at 0 degrees as well. 0 degrees plus T12 is an internal node. Plus T23 is on the boundary. T23 must be up at the top that I've clipped off. It is, it's 100. T23 minus 4T22 plus T21 is on the boundary. T21 is not on the boundary, it's an internal node. Apologies. T21 is equal to 0. So we have T12. See this T21, I'm just going to write that one first. T21 minus 4T22 is equal to minus 100. Okay, last equation is this one up here, T22. T22, I believe, is an internal node. T22, on a wee bit high there. Plus TO2, TO2 is on the outside. That is on, yeah, on the left hand side, temperature B, 150. Right, plus 150. T13 is on the top, is 100. Minus 4T12 plus T11 is equal to 0. And now we can rewrite this. We'll go for T22 plus T11 minus 4T12 is equal to minus 250. All right, so from this here, we can write up our form of AX is equal to B. Tell you what, I've kind of really over exaggerated the distance needed between X and B. Alright, so what we'll do is I'm gonna be careful to arrange these in a particular way, because I want to make sure to have diagonal dominance. You see the magnitude of the element in each row that exists on the main diagonal of the coefficient matrix A must be larger in magnitude to than the sum of all other elements in that row, not including the that diagonal element again. So obviously I don't want a 0 on my main element. So my first equation here, I have T11 is going to give me, I can solve for T11 first, because in my first equation here, that'll put my minus 4 on my main row. What I can then solve for here is a T21, say, And my next equation, I should put that into the second row, T22, and finally a T12. Let's see how we go with that. Let's see if I can write them up on the lines a little bit better. T11, T21, T22, T12. Let's see how we go. So in A, see my T, how many T11s do I have in my first equation? I have -4 T1s. T21s, I have one T21. T22, I have no T22s. And the T12, I have one T12. Next equation, right? My T11s, I have one. T21, I have -4. T22, I have 1, T12, 0. Next equation, third one, T11s, I have no T11s. T21s, I have 1. T22s, I have -4. And T12s, I have 1. And finally, on my last equation, T11s, I have 1. T11, T21s, I have 0. T22s, I have 1. And T12s, I have -4. This coefficient matrix, system response, column vector, and that's equal to the forcing vector. Forcing vector then are just going to be our results here. -350, -200, -100, and -250. Right? Same order. Okay, same order. T21s, T22s, -4, and T12s, yes. Okay, so for diagonal dominance, we need to say there that the magnitude of the element of the coefficient matrix, and call it A, where I is equal to J, so 1, 1, 2, 2, 3, 3, 4, 4, has to be greater than the sum of the elements of the elements IJ, where I does not equal J, right? So that's it. So our main elements, this here again is going to be the element in each row that exists on main diagonal. Right? And this one here is going to be this is the sum of the elements on each row not including the element on the main diagonal. Okay, so we could see, because it's a very simple matrix, we're not dealing with very difficult numbers. These are all obviously magnitudes, not dealing with many numbers or difficult numbers. That it's 4, the magnitude of the element on the main diagonal on each row is 4. Row 1, it's here. Row 2, this is on the main diagonal. Row 3, this third element's on the main diagonal. Row 4, the fourth element's on the main diagonal. So 4 in all cases must be greater than, so the magnitude of -4, which is 4, must be greater than the sum of the magnitudes of the other elements. Sum of the magnitudes of the other elements on the first row is 1 and 1, which is 2. 4 is greater than 2, check. Second row, 1 and 1 is 2. 4 on the main diagonal is greater than the sum of the elements in that row not on the main diagonal. 4 is greater than 2. Row 2 check. Likewise for row 3, 4 is greater than 1 and 1 is 2. And likewise on row 4, 4 here, which is the element in the fourth row on the main diagonal, is greater in magnitude than the sum of 1 and 1, which are the other elements in row 4, which are not on the main diagonal. Okay, so we could see, we can see that for each row, for each row, 4 is the magnitude of the element that exists on the main diagonal. On the main diagonal. Four is greater than the sum of the other elements in each row. So you could really formalize this. We're really going to town on it here, probably too much. Row 1, 4 is greater than 2. Row 2, 4 is greater than 2. Row 3, 4 is greater than 2. These are just the 1 and 1. These are the other elements not on the main diagonal. Row 4, 4 is greater than 2. Therefore, I could say that therefore the system is diagonally dominant. Okay, part B, that's part B done. All right, so for part C, we're asked here, use 3 iterations of the Gauss-Seidel method to solve for the temperatures of the internal nodes. Clearly state your initial guess and your final solution. So my suggestion on this is that we go into MATLAB and do it a little bit. It will be a little bit quicker, a little bit less tedious than all of this writing. Yes, I do know that MATLAB obviously has linsolve and has other native functions that could be used for solving systems of linear equations like this, but it's never as fun as writing up kind of your own code or your own algorithm. So let's give it a go here from scratch. I am going to just kick off into MATLAB here and move the mug back over to this side. Let's go for a new live script. Let's try a text, come on into a heading. Right, let's go to the title. So I'll go for Gauss-Seidel. This is Numerical Methods for Engineers 2026 Q1. Let's put a section break and let's go for parameters, which will really be our boundary conditions. Alright, so the parameters on this, let's see, can we even bring in something that will leave this, right. Let me just hold this like this. It's, yeah, try it like this. I took a screenshot, oh, there we go. Right, this workspace will be a bit tighter. Alright, the only reason I wanted to do that is because I want to not have to flick back and forth so much. Alright, parameters. So the parameters here, what I'm going to write in is parameters for my boundary condition. Let's go for TO1 is equal to, so TO1 is equal to B, and B is 150. So TO1 is equal to 150, TO2 is equal to 150. Let's go around, just going to go around clockwise. T13 is on side A, which is equal to 100. And T23 is equal to 100. T32 equal to 0. T31 equal to 0. And T10 is equal to C, which is 200. And T20 is equal to 200. Grand job. Right, so having that now, we can then move into maybe a next place here. Let's try section break on this. Take ourselves into text and let's put into let's see results, or let's say computational facilities. There's things there to make what we're doing a little bit handier. I'm going to come into code and we'll write in our put in a storage space here. Let's call T. Let's make a matrix of a. I'll tell you what. Before we do that, just check what our error needs to be. Use three iterations. So we're told actually how many iterations we need to run. So that is discrete. We need to use 3. So we're going to use a for loop in this, as opposed to running a while loop to iterate until we achieve a certain allowable error. So we're just going to use 3 iterations. So let's put that into here. Let's go for max iter is going to be equal to 3. Now let's create a matrix there, a storage matrix. We're just going to call T of temperatures, which is going to store my internal node temperatures from iteration to iteration. So I'm going to write this here in the format that I'm going to have 4 rows. Each row is going to represent one of the internal nodes as one of the formulas. And then each column there is going to represent an iteration. And I'm going to start with my first column being my initial guess. So, and I need 3 iterations, so I need a total of 4 columns, an initial guess, and then 3 iterations. So let's go for zeros. Right, I'm going to go for 4. 4 rows for 4 internal nodes, and then I'm going to go for max iteration plus 1. Okay, now what I'm going to do is I'll write in my first column values. Okay, I'm going to put in as my initial guess. I'm going to just do all zeros. 0, 0, 0, 0. Probably be no harm to put some commenting in. This is specified by question. Alright, this is I'm going to call this a results storage matrix. What I'm going to write in here is just to help me remember whenever I'm coding these. And I say R1 is going to be solving for, let's check what I have. R1 is solving for T11. So what do we have coming up here first? Yeah, I'm going to go with these ones, T11, T12, right? So R1 is equal to T11. R2 will be equal to T, that's gone already, 12 and then 21, T12. R3 is equal to T21. And then R4 is equal to T22. All right. Let's make sure we're good with that. T11, T21, T20, T11, 21, 22, and then 12. T11, 21, 11, 21, just double check. 11, we'll do it this way. 11, 21, 11, 21, 22, and then 12. The reason I had it the other way around was because I had altered it so that it would come out. So I would solve it and I would present it as asked here, T11, T12, 21, and 22, which is not the way it lends itself for the diagonally dominant system. So I have it written back here the way that you normally would write it for the diagonally dominant system, which leaves the 4s on the main diagonals, 11, 21, 20, 22, 12. Leaves them higher values on the diagonal, which is what we want. So that's going to give us into there, and this is going to be our initial guess. Initial guess for, or not for, it's of, 4 of, temps at internal nodes. Alright, grand. Okay, let's go on into a section break. Let's write in text and let's put in a calculation. Let's back into code and we're writing this in a for loop. So for I is equal to 1 up to our max iteration. It's going to be doing 3 of these. And I'm going to have to code in our a couple of formulas. So what I'm going to do is I'm going to take them from here. I'm going to put them in their orders. So not specifically here. So again, these are being presented very specifically for, because the question asks for a T11, T12, 21, and 22. So I just want to make sure that I write these in the order that I have the matrix set up for and the diagonal dominance is present for. Right? So in our first one here, I'm going to go for T11. I'm going to write up T11 here first. Okay, so let me just drop that down there. So T in my first row, and then I'm going for my I plus 1th column, which is in my second column. Right, this is going to be the formula for T11 is my first one, is 1 divided by 4 multiplied by, now T21, do we have a T21 in here? T21 is in R2, so I'm going to go for T2 of I, because I need to get my initial guess value for here, which it exists in I, T2 of I plus T01, which I've specified up here, plus T01 plus T12. Again, T12 is an internal value. T and T12 is going to exist in R4, 4 of I plus T10. Right, there's my first one done. Next one is T. So the next one that I'm looking for here is going to be R2 is T21, which is this formula here. Third one down. T2 I plus 1 is equal to 1 over 4 multiplied by, so again this is the third one down because we're shooting for T21. Row 2, T21 is equal to T31 plus T11. Now we already solved for a T11, right? So this is T1 of I, because Gauss-Seidel, we're going to use the latest values as we move forward. If this was Jacobi, we'll go for, I plus 1. I was thinking of I minus 1s there. If it was Jacobi, we were going for I here. We'll be doing everything based on our previous values, but for Gauss-Seidel, we update our values as they become apparent. So T11 plus T22, which we haven't solved for T22 yet, so it's still going to be T and 22 exists in R3. And that's still I, plus finally T20. Okay, next one is T, my third row. Third, I plus 1 is equal to, so in my third row, I'm solving for T22, which is this equation here. Last one, 1/4 multiplied by T32 plus T12. Now, have we solved for a T12 just yet? No, T12 was in my fourth one. I haven't done a T12 yet. So this is T4 of I plus T30, 22, yeah, T12, T23 plus T21, and We have not solved for T21 just yet. Oh, we did. That's R2. Sorry. Yeah. T2 I plus 1. Round quarter. Close, opened. T31. That's it. And then finally, T for 4I plus 1 is going to be equal to 1 over 4 multiplied by, right, so my fourth one here, I'm solving for T12, which is this top one, T22 lives in R3, which I've solved for. This is T3I plus 1, I have that value, plus 12, this one, T02 plus T13 plus, last one is T11, which is T1I plus 1. Okay, let's run that, and then we can display T, or just output T. Let's put it out as a variable, so we can just see it here. We can open it up. Come on up. There we go. Nothing. This is just, try that again. Open it here, actually. Be a wee bit handier to see. Alright, so this is our initial guess, all zeros. After our first iteration, we calculated these values. Our second iteration, we calculated these values. And then in our third iteration, we calculated these values. So if we were to present a clear response, or a clear indication of what our initial guess was and what our final values were, clear state your initial guess and your final solution, we would be showing column 1 and column 4. Not that would have anything to copy and paste if this was a paper-based workflow, but this is our initial guess, and this is our final solution after 3 iterations. Now clearly we should have kept iterating. These are not the temperatures. It's too big of a jump to say that we are anywhere near the final temperatures. But what we could maybe do is try more realistic starting point temperatures, just as an exercise, to see what the effect there on that convergence might be. So if I was to shoot, and just shoot that one, I'll close there. And if we were to update, say, our initial values here, let's go for all 90s. To run that again, and if we were to output T one more time, we could see a much quicker convergence here on T11, 132, 143, 142.43, 143, 104 to 105, 79 to 80, yeah, 117 to 118. Looks pretty good. You know, they're sort of converging an awful lot faster there, which would be expected because our initial guesses would be much higher, much closer to what the final values are. So yep, I'm going to leave it at that, and hopefully that was informative in some way. Again, I probably could have left it a wee bit clearer, I think, by not changing the order in which that these were presented versus the order then in which they were coded. Again, I probably read a little bit too much, and I stuck a wee bit too strictly to this being shown as T11, 12, 21, and 22, which I'm sure in this exam, if you did show it as a T11, T T12, T22, T21, or any other order. It really wouldn't have mattered. So yeah, thanks again for joining in the video. If you haven't already, do hit please subscribe, and we'll keep going with these numerical methods for engineers videos. If you have any queries, or you'd like me to look over any particular method, or you have any application, yeah, please send it over to me anyway, and if you like, we can get a video on it and maybe look at a different way of solving it. So thanks again for your time. Good luck.